Hello, welcome to this presentation. My name is Muhammad. I'm from Bournemouth University, and today I'm going to talk about a location-aware authentication model to handle uncertainty in Internet of Things. The agenda for this session is that first I'm going to talk about the background of our research. Then I will introduce the research challenges. Next, I will give you a brief introduction about the state of the art literature. Methodology and design will come after. Then, I will discuss the results of the research. And finally, I will conclude our research and I will talk about the future direction of this research. Internet of Things has a number of inherent characteristics like scalability, heterogeneity, and dynamism. These characteristics introduce both opportunities and challenges. Among known challenges, authentication remains as a crucial and open challenge. Authentication in IoT is affected by some characteristics like, for example, dynamism may affect on authentication because of the need for tracking rapidly changes of entities and environment attributes like joining and leaving nodes to the environment or displacing of entities. Scalability by considering more participants through expanding connectivity from human to machine communication, or by heterogeneity, the need for handling interoperability issues derived from integrating different platforms and networks. In addition to the mentioned challenges, our focus is on a novel challenge called uncertainty. Uncertainty in authentication is defined as a state in which it is not certain whether authenticating a subject leads to a security incident. Uncertainty is caused by the lack of information about the likelihood of the incident occurring upon authenticating a request. Part of the mentioned characteristics for IoT amplify uncertainty in authentication. For example, the lack of information for access decision caused by inability of tracking entities in highly dynamic environment like IoT. The lack of information for access decision caused by network delay or disruption due to the technical challenges like missing reading in RFID or WSN technologies caused by collision, or data inconsistency caused by reading data from multiple resources regarding the same object, or ghost data caused by frequency reflection. In this research, we have analyzed both traditional and emerging access control models against evaluation criteria to see whether or not they are applicable to a highly scalable, dynamic, and heterogeneous environments like fog computing, for example, in the context of IoT. As shown in the table, the most adjustable security access control model is attribute-based access control model. And as you can see, it has extensibility, heterogeneity, dynamism, and context-aware characteristics. A number of studies suggested resilient access control paradigms to deal with indeterminate data access scenarios. These paradigms include break the glass access control, optimistic access control, and risk-aware access control. Both break the glass and Optimistic access control paradigms suffer from scalability and heterogeneity issues. For risk-aware access control model, as we did a comprehensive survey, it does not fit in highly scalable, heterogeneous, and dynamic environment like IoT because of the following reasons. First of all, it suffers from the limitation of periodic assessment in highly dynamic environment like IoT. Second, it suffers from the lack of knowledge about the entities in a scalable environment like IoT. And third, it suffers from the interoperability and dependency challenges in such a dynamic environment. As mentioned earlier, thanks to its characteristics, attribute-based access control model was chosen as our reference model to build our prediction data model based on it. Prediction model is trained and built using a dataset which consists of uncertainty values for three attributes: time, location, and credential. As you can see in the right figure, it's a matrix consists of those three attributes. And as you can see in the left picture, prediction model should be placed at uncertainty engine. It is responsible to calculate the uncertainty of the authentication requests. One of the requirements for this project was a dataset to train and build our prediction model. Finding a real dataset in the field of access control for both authentication and authorization is a tough challenge. That's why we have synthesized our dataset based on the state-of-the-art relevant studies. Our dataset consists of uncertainty values for three attributes: time of the request, location where requests come from, and the credential of the subjects. The size of the dataset is determined by 5,000 records in order to avoid overfitting. And also, the value for the time of the authentication request were generated using multinomial and normal probability density function based on the chosen business model. The values for the location of the requests were generated using a mixture of Gaussian PDF. We have also considered multiple points of interest and corresponding uncertainty areas in order to make the scenario more realistic. The values for the credential were generated using multinomial PDF to cover all possibilities. Uncertainty values for the time are assigned based on the business logic of the service under which we want to build our prediction model. Based on our case study, we assume that the service is available during work hours, 9 a.m. to 5 p.m. So, authentication requests during this period is less likely leads to an incident than after 5 p.m. and before 9 a.m. in the morning. Uncertainty values for the location are assigned based on the 3 points of interest, which is defined geographically. According to our case study, authentication requests which come from and around the first point of interest are less prone to be flagged as incident than second and third POIs. Authentication requests which come from and around the second point of interest is less prone to be detected as incident than the third point of interest. Uncertainty values for the credential are assigned based on the status of the credential provided by the user during authentication phase. If requester provides both username and password correctly, user will be assigned the least amount of value as uncertainty. If user provides correct username but incorrect passwords, the higher value of uncertainty will be assigned. And finally, if user provides incorrect username, he or she will be assigned the highest value as uncertainty. We have applied 3 classifiers including k-nearest neighbors, random forest, and neural network to build our prediction model with. We have also validated the prediction models using tenfold cross-validation method. The performance of the prediction models were compared using the following criteria: accuracy after cross-validation, precision, recall, F1, receiver, and operator characteristics, ROC, and also area under the curve, AUC. We have also introduced noise to our dataset during training to make the case study more realistic. The table shown on the top right side provides the values of accuracy for these 3 classifiers. This slide provides figures and statistics for noiseless dataset. And as you can see here, random forest and neural network show the best performance in terms of accuracy at rate of 86.92%. The table shown on the bottom left-hand side provides the accuracy rate, precision, recall, and F1 for a neural network classifier. As you can see here, we have developed 4 different neural network architecture, including single layer, 1 hidden layer, 2 hidden layers, and 3 hidden layers. As we mentioned earlier, the best results to be obtained for 1 hidden layer with 30 neurons. On the bottom right-hand side, you can see a figure of a ROC curve. And here you can see that the random forest curve dominates the other 2 curves. By associating noise to our dataset during the training phase, you can see the contrast in the results. As shown in the table, the best accuracy achieved for random forest classifier at rate 82.20%. In the table for neural network, the best results in the noisy environment achieved from single layer neural network. Table shown on the bottom left-hand side includes accuracy rate, precision, recall, and F1 values for our neural network classifier, which is trained and tested by noisy dataset. And as you can see here, the best result is for a single layer architecture at rate of 80.08% of accuracy. As can be seen on the bottom right figure, the most area under the curve is for neural network classifier. Despite the fact that several approaches have been proposed to address scalability, dynamism, and heterogeneity of access control in IoT, uncertainty in authentication remains as a neglected challenge. We have proposed a novel data-driven model as the extension of attribute-based access control model. Our model is able to handle uncertainty of mobile users' devices as well as fixed one in IoT. The model was built using three robust classification algorithms, namely k-nearest neighbor, random forest, and neural network. The results showed that the prediction model created by random forest classifier is more accurate than the other using both noisy and noiseless dataset at accuracy rate of 86.92%. The designated model can be run on constrained resource entities as we ran it on Raspberry Pi machines, and it can be deployed on a scalable and heterogeneous environment without limitation. Thank you for your attention, and please send your questions to my email address at mhaydari@bournemouth.ac.uk.